Now we go into the understanding of module 4, and the contents of module 4 are as follows. So here we will look into sequential circuit design and dynamic logic circuits. In the earlier topic, that is module 3, we had a discussion on combinational circuit design. Right now we are considering the sequential circuit design, which is based on one input following the one input giving us the output, and that output is fed as input to the next circuit. So the basic topics involved in sequential circuit design is it requires memory, and the circuit design, it is the important concept used here are the latches and the flip-flops. And next you have dynamic logic circuits. So this is almost the same as your CMOS, but then extended version of CMOS here with the influence of the capacitor being introduced here. So that is what we will be discussing here in the next topic. Right now our focus would be on sequential circuit design, which is introduction, circuit design for latches and flip-flops. So next we have seen how successfully the latch was constructed. Now we will see in terms of data path applications. What is a data path? Data path is the ALU plus the register. So in data path applications, where input noise can be controlled, the inverting latch of figure H may be preferable because it is faster and more compact. So exclusive, there are n number of latches. Depending on the type of applications, the appropriate one is chosen. So in data path application, the primary concern here is the input noise should be controlled. So input noise should be controlled, and the inverting latch of figure 6. So already we have seen this is preferable in data path applications, and Intel uses this as a standard data path latch. This is very commonly used in this company Intel. Next, the next diagram, figure I, shows the jam latch. So this is almost the modification of variation of figure G, where we had the earlier diagram, which reduces the clock load and saves two transistors by using a weak feedback inverter in place of a tri-state. So you have, notice here the two inverters are of different size, and in the feedback you have a weak feedback inverter which is of a smaller size. So this has a better application which is specific to its own application. This is called as a jam latch, which reduces the clock load and saves two transistors by using feedback. Next you have another type of jam latch which is commonly used in register files and field programmable gate array cells. So this is also another type of jam latch. Many such latches read out onto a single D-out wire, and only one latch is enabled at any given time with its read signal. So there is an Itanium processor which uses this latch as shown here, given in figure K. And the static feedback, the pull down stack is closed but the pull up is weak PMOS transistor. When you look at this in the static feedback, you have the static feedback here. The pull down stack is closed. Based on this output, the pull down is closed and one is given to the transistor. The stack is clocked, but the pull up is a weak PMOS transistor. It is a weak PMOS transistor. Therefore, the gate driving the input must be strong enough to overcome the feedback. When the input with the input inverter, the latch can be viewed as a cross between the designs shown in G and I. Can be shown between the designs shown in G and I. So there is an improvement about this with respective to G and I. Some latches add one more inverter to provide both true and complementary outputs. So still latches are added, and one more inverter is added in order to get correct output, and since this is complementary, this also has to be rectified. So anyhow, the latches can be designed as per the choice and the application required. Next we have another type of a latch in figure D here, which can also be drawn as clocked tri-state as shown in figure. So this is your almost your tri-state inverter. Okay. So you have an inverter. With the inverter you have two clocks which are complementary. So you have two inverters. This is your inverter NMOS and PMOS with a common input D, and the output is taken in between the two clock signals where they are given to the two more inverter stages. So you have Q bar here. This is the dynamic latch, which is drawn as a clocked tri-state, or in other words this is also called as a tri-state inverter. Such a form is sometimes called as clocked CMOS or C square MOS logic. It is not C2, it is C square. You should read it as C square MOS logic. What exactly happens in this? The conventional form using the inverter and the transmission gate, earlier one, is slightly faster. It is fast because the output is driven through the NMOS and PMOS working in parallel. Either one of them will be working, and right now they are working in parallel. Both of them will be on at a time or both of them will be off, not like the CMOS working. Therefore, you will have the fast transmission. But when you look or compare with C square MOS, is slightly smaller because it eliminates two contacts. You have only one output and one input. So all of the latches shown so far are transparent while phi is high. So when phi is high, 1 bar 0, 0 bar is 1. Therefore, you have active low latches when you are swapping between phi and phi bar. Of course, this will be almost the representation of a tri-state inverter. Next, we look into the topic which is called as conventional CMOS flip-flops. So we are familiar with flip-flop, which is dealt in your primary semesters. Now we have with CMOS logic the flip-flops. So now you have this diagram. What is this diagram? You have one inverter, one transmission gate, one inverter, one transmission gate, one inverter, and finally your output. So figure A shows a dynamic inverting flip-flop built from a pair of back-to-back dynamic latches. So this in turn is nothing but a flip-flop which is built using dynamic latches. So this thing is your dynamic latch, and when you combine them it gives rise to a inverting flip-flop. The output is Q bar, because there are three stages of inverters, and therefore the signal is inverting. If you had even pair that is 1, 2, 3, 4, 4 such inverters, you would have it as non-inverting. Therefore, in conventional CMOS flip-flop, either the first or the last inverter can be removed to reduce delay at the expense of greater noise sensitivity on the unbuffered input or output. So you can remove this at the input or at the output, and by removing so the noise sensitivity is better and delay is also removed on the unbuffered input. So right now the input is also buffered, the output is also buffered. Either one you follow, it would give you a better result. Next we have different type of a circuit where you have the feedback path associated. So figure B adds feedback and another inverter to produce a non-inverting static flip-flop. So you had an inverting flip-flop output, but here trying to get a non-inverting output. However, some of the alternatives described later will be much better. So by doing so or adding a feedback and another inverter, see here as I told you 1, 2, 3, 4, you will get a non-inverting signal. Flip-flops usually take a single clock signal phi and locally generate its complement. So that is the flip-flop is going to work. Generally it accepts only the clock pulse, and internally it is going to generate the inversion of the clock pulse. If the clock rise or fall time is very slow, it is possible that both the clock and its complement will simultaneously be at intermediate voltages, making both latches transparent and increasing the flip-flop hold time. So if the rise and fall time is slow of the clock, both the clock and its complement will simultaneously be at intermediate voltages in between. Therefore, latches are transparent and therefore the hold time is increased. So the clock is complemented and buffered in the flip-flop cell to sharpen up the edge rates at the expense of more inverters and clock loading. However, the clock load should be kept as small as possible because it has an activity factor of 1 and thus accounts for much of the power consumption in the flip-flop. Next, some of the flaws in the flip-flop are it has an internal race condition between the two latches. So you have one latch here and another latch here. This race can be exacerbated by skew between the clock and its complement caused by the delay of the inverter. So you have some problem in this called as internal race condition that can be rectified by using a built-in clock inverter. So inside you are trying to have a clock which is being built inside. You have phi is the only thing internally. Phi bar is generated and that is what you have here. So the problem of race current condition can be rectified by having a design as shown here. So when phi falls, both the clock and its complement are momentarily low as shown in figure B. When phi is falling down, phi bar should be, phi is falling down means when phi is 1, phi bar should be 0. So this is also falling and this is also low. So when phi falls, both the clock and its complement are momentarily low. At a moment it is low. This is as usual, it is low. Since this is falling, it also comes to low. At this particular point, both are low. Turning on the clocked PMOS transistors in both transmission gate. The moment this goes to 1, PMOS transistor is becoming high. If the skew in other words is called as the inverter delay. If it is too large, the data can sneak through both latches on the falling clock edge, leading to incorrect operation. So we are trying to modify the structure in this version. Next, figure C shows a C-square MOS dynamic flip-flop built using latches rather than inverters and transmission gates. So you have a device which shows a C-square MOS dynamic flip-flop. You have the flip-flop which is dynamic, which is got with the help of latches rather than inverters and transmission gates. So you see there are no transmission gates and inverters are there, which is meant only for complementing the clock pulse. But everywhere you find the latches, or in other words flip-flops. This is somewhat a design which is better claimed by the author because each stage inverts, data passes through the NMOS stack of one latch and the PMOS of the other. So skew that turns on both clocked PMOS transistor is not a hazard. So in each stage data passes through NMOS stack. You can analyze with respect to the clock being 1 and 0, and PMOS transistors are not considered as a problem. However, the flip-flop is still susceptible to failure from very slow edge rates that turn both transistors partially on. So the same skew advantages can apply even when an even number of inverting logic gates are placed, and this technique is sometimes called as no race. So skew advantages apply even when an even number of inverting logic stages are placed. In practice, most flip-flop designs carefully control the delay of the clock inverter, so the transmission gate design is safe and faster than C-square MOS logic. So when you have flip-flops design implemented, you have better design and faster design compared to C-square MOS logic. So next we have the flip-flop designs which are still present potentially minimum delay problems. All these flip-flop designs still present potential minimum delay problems between flip-flops, especially when there is little or no logic between flops and clock skew is large or skew analysis is too much. Work and performance is less important. A reasonable alternative is used to use a pair of non-two-phase, non-overlapping clocks instead of clock and its complement. So instead of using clock and its complement, we will use non-overlapping clocks. So when one of the clock pulse is high, the other clock pulse is low. They'll never overlap, and that gives you a better design as claimed by the author. Better design in terms of clock skew analysis, work and performance. So the flip-flop captures its input on the rising edge of phi 1, and by making the we'll see this in the next slide. By making the non-overlap large enough, the circuit will work despite large skews. However, the non-overlap time is not used by logic, so it directly increases the setup time and sequencing overhead of the flip-flop. The layout for the flip-flop is shown on the inside front cover and is readily adapted to use a single clock. Observe how diffusion, we'll look into